So, we have discussed that how to represent a transformer by an equivalent circuit and how to measure the parameters of the equivalent circuit by open circuit and short circuit test. So, we have seen that if the transformer is under open circuit condition, that means open circuit condition, then equivalent circuit is simple, one shunt circuit. This is the voltage V1 I am giving. This voltage V2 will be available, but no load. So, this is the open circuit condition, very simple representation of the transformer. This type of representation is used to calculate the core losses of the transformer and also the behavior of the transformer in the transient condition. If the transformer is fully loaded, if I want to find out the full load conditions, how it behaves, that means what is the regulation of the transformer, how it will be behaving with the load, then we represent the transformer with the second form, that means loaded condition. Loaded condition transformer will be represented by a resistance and inductance. Only ignoring the magnetizing the shunt branch. It will be just a series representation of the circuit if I want to find out the behavior of the transformer at different load condition. But if I want to find out the efficiency of the transformer, then I will have to use both the form efficiency. Then for efficiency, we will use both the forms of the transformer. That means this series impedance will be there and also the shunt also will be there, because shunt will account for the core losses, series will account for the copper losses. So, both the losses will be represented. And while studying the efficiency of the transformer under different load condition, under different load power factor condition, we will use the shunt series. This is called shunt representation, this is called series representation, this is called shunt series representation, combination of both. But we know Thevenin's theorem, any circuit can be represented by a Thevenin voltage source and also a Thevenin impedance. Any circuit can be represented and then its value, its load condition, that means load current can be found out very easily by applying the Thevenin condition. So, we can also Thevenize the transformer. That means, I have got a transformer. Number 4 is Thevenin equivalent. What is Thevenin equivalent? I have got a transformer. This is the primary side, this is the secondary side. So, Thevenin says this is this thing. If I want to represent it, I will have to open this secondary terminals, and have to find out what is the open circuit voltage. You know, under no load condition, the open circuit voltage, when I apply rated voltage at the primary, then what is the open circuit voltage? That V2 is Thevenin voltage. That means V Thevenin is actually V2 when I apply at the primary rated voltage. So, what will be the Thevenin impedance? That means Thevenin's impedance. That says that you short circuit this voltage source, and then find out from this open terminal what is the value of impedance. That impedance you can very well understand, that impedance is secondary impedance. That means primary impedance referred to the secondary plus secondary impedance will be the V Thevenin. That means impedance of the transformer, impedance referred to impedance of the transformer referred to secondary. So, when we will use transformer in a circuit where this secondary is being used as a voltage source, and then you are developing circuit for certain purpose, then you can Thevenize the transformer like this by open circuit voltage V2 and this Thevenin impedance, which is nothing but secondary impedance of the transformer. So, impedance of the transformer referred to secondary. So, this way we can Thevenize the transformer. So, fifth condition is we can even look at the transformer as a two-port network. We have got one port, one pair at the primary, one pair at the secondary. So, I can represent a transformer so this may be the black box and these are the two ports. So, here voltage is V1, current is I1, here current is I2, voltage is V2. So, in many cases, especially the problems of transmission line problems, transformers may be represented and most commonly represented by a two-port network with the famous expression V1 will be equal to AV2 plus DI2 and I1 will be equal to CV2 plus DI2. That is your famous ABCD representation of a two-port network. So, a transformer can be represented by this equation with ABC parameters also. Another point should be mentioned. The transformer generally when you are using for transmission purpose, distribution purpose in a plant. So, we are operating at 50 cycles. So, there is no problem with our equivalent circuits by representing the whole transformer by resistance and reactance. But if the transformer is used in electronic circuit for communication purpose, you know for a communication any signal may be decomposed with lot of harmonics. If I decompose a signal into harmonics, there will be lot of high frequency harmonics will be there. That those harmonics, when frequency is becoming high, you may not be able to represent the transformer with lump parameter. Then you will have to represent the transformer as a distributed parameter. At the very high frequency, we will have to represent the transformer as a distributed parameter. So, inductance, resistance will be negligible, then inductance will have to be represented at the distributed parameters, and under that condition you will have to consider the capacitance of the transformer. How capacitance coming? You know when the windings are made, two conductors separated by the insulation of the winding wire or winding conductor, whatever you say. So, between these two conductors there is the insulation layer. So, that will give rise to interwinding capacitance. So, in the transformer that capacitance actions will be felt at the higher frequency only. At lower frequency that impedance is so large that it does not have any effect on the performance of the transformer. But in the high frequency range, when you will be operating with this transformer, you will have to take into account the capacity effect, that means interwinding capacity effect. Then capacitance will be there, because core of that means ferromagnetic core of the transformer is always grounded. So with that, our winding is a conductor. These current sheets are there. So windings and the core will also form a capacitance. So that capacitance is also will be required to be considered. So at high frequency range, that means sixth type of representation of the transformer, that is at high frequency range, at high frequency, you will have to represent the transformer as a distributive element. Resistance will be very less, and between these windings there will be capacitance. Lot of capacitance will be there. And between this is maybe the core, which is grounded. Between the core and the winding there will be capacitance also. So this will be the model of the transformer at the high frequency if I operate it. But one thing should be remembered always, that while discussing the transformer, we have used actually Faraday's law to understand the working of the transformer, how voltage is getting induced, and how this induced voltage from the secondary is transferring power to the load. But you should know that we can look at the same transformer as a coupled circuit. We all know the coupled circuit, magnetically coupled circuit. Transformer is nothing but a magnetically coupled circuit. So from purely circuit theory point of view, because field theory is this, Faraday's law is a part of our field theory through which we try to understand the working of the transformer. But if you look at the transformer purely from circuit theory point of view, then we can say that primary will have its self-inductance, secondary coil will have its own secondary inductance, secondary coil will have own inductance, self-inductance, primary will have its own self-inductance. So there will be inductance in the primary, there will be self-inductance in the secondary, and both this coil will be coupled by a mutual inductance. So we can represent the transformer from mutual inductance point of view. So that is that we can have the same resistance will be there. Of this is the primary resistance, this is the primary leakage reactance, and then this is your mutual inductance of the transformer. This is the resistance of the secondary, this is the self-inductance of the leakage reactance of the primary. So this is actually the equivalent circuit of the transformer from the purely circuit theory point of view. Now, what will be the mutual inductance? If my total mutual inductance, when this number of turns on both the sides are same, is M, then my actual mutual inductance will be alpha into M, where alpha is the voltage ratio or turns ratio of the two transformer coil, that means primary and secondary. Now this is the resistance of the primary, say this is R1. So what is the leakage reactance of the primary? Leakage reactance is the primary is the self-inductance of the primary minus the mutual inductance. That means whatever is self-induced EMF will be there, minus the mutually induced EMF. If you do the subtraction of that, you will get the representation of the leakage reactance. So, what will be the leakage reactance? Leakage reactance will be L1 minus alpha into M, where alpha into M is the mutual. That means this is the mutual flux and this is the self-induced reactance of the coil. So, next is the secondary side. Secondary side, every quantity will be referred to the primary side. So, it will be R2 dash. What is R2 dash? R2 dash will be alpha square into R2. What is the leakage reactance? That will be L2 dash. That means I can say L2 into alpha square minus alpha into M. That means L2 into alpha square is the self inductance of the secondary coil referred to the primary, and minus this mutual inductance will be the leakage reactance of the secondary. So, leakage reactance of the primary is L1 minus alpha M, and leakage reactance of the secondary is L2 alpha square, that means I am referring it to the primary, and then minus alpha M will be the leakage reactance of the secondary. So, this is the representation of the transformer from mutual inductance point of view. So, at the different application, we will be using different types of equivalent circuit, which gives us the most practical and useful, at the same time accurate solution of our problem. So, in the next class, we will be discussing about the losses of the transformer and its efficiency.